Hi, welcome again. Today's chapter is on electric currents, electricity. Now, it's not so much that electricity was discovered per se, more so it was understood, where it comes from, how it's generated, how to store it and control it. So, to understand the gist of an electric current, you can see sparks are flying left and right here. To understand the nature of electricity, it all starts with a charge, and they have to move, but not just move randomly. See, if we took a piece of wire, let's just say my pen here was a piece of wire, a copper wire, and we could look at the copper atoms in this length of wire, maybe about 6 inches or so, we would count trillions upon trillions of atoms. Now let's just say that each atom can surrender or give up just one electron. Now the thing about conductors is that they've got these outer electrons, electrons in their outermost shell, they're called valence electrons, that are very weakly bonded to the nucleus of their host atom, so they're free to move from one neighboring atom to another. And so these valence electrons, they sort of jump ship, if you will. They don't really have a specific home, and they have many homes, and trillions of homes. So at any given moment, if we can use a high-power microscope and we could see the electrons all jumping left and right throughout this length of wire, it's all completely random motion. And by the sheer numbers involved, if we were to pick a random direction, let's just say in this direction, the millions of electrons that are randomly moving in this direction at any given moment is just about balanced by the number of electrons moving in the exact opposite direction, this way, at that same given time. So the net flow of charge, if you will, is zero along this direction. So that's not what constitutes an electric current. Now, we need a way to have all of the electrons, while they're undergoing their chaotic motion, which is very fast, by the way, very close to the speed of light, as they're undergoing their chaotic motion, we need a way to cause all of the electrons to drift in the same direction. And we do that by applying a potential difference, sort of a force, if you will, maybe an electric field or a battery, to cause all of the electrons, while they're undergoing these chaotic motion that never stops, to do it while they're drifting crazily like this, in one particular direction. It is that net flow of the chaotic motion, what's called the drift velocity, that constitutes an electric current. And that actually happens much, much slower than the chaotic motion. Like I said, the chaotic motion is maybe 10 to the 5th power meters per second, whereas the drift velocity is, just the opposite, maybe about 10 to the minus 5 meters per second. The thing is, once an electric field is applied, some generating force is applied to cause the electrons to drift in the same direction, they all drift at the same time. This is why it's almost instantaneous. When you flip a switch, it turns on the lights in the room, even though the energy has to flow from electron to electron throughout the entire length of the wire to get to the bulb. So it's not that one electron moves and it causes the other guy to move and the other guy to move. That would take a very long time. There are trillions of electrons. So obviously that can't be happening. All the electrons begin to drift at the same time, so the electric current generation is almost instantaneous. So in essence, that's the nature of an electric current. And so when we start this chapter, if I pull up the chapter here, the very origins of where these what are called conduction electrons originate from, and it turns out they are the outermost electrons in any given atom. And this works well for metallic atoms, materials, because their outer electrons, their valence electrons, very weakly bonded. And so with the slightest of agitation, and in particular, when they're brought close to other neighboring atoms like their own kind, new energy levels, what are called conduction bands, begin to become evident. And these valence electrons now jump to these conduction bands. And in the conduction band, they're free to move. It's like an electron highway if you will. So they jump from conduction band to conduction band. That's the chaotic motion that ensues, and if we can control that chaotic motion to all happen in the same direction, it creates an electric current. So metals are great conductors. Silver, actually, the metal silver is one of the world's, if not the world's, greatest conductor. Pure silver, that is, but silver, it tarnishes, it rusts very easily with the atmosphere, and it forms a layer of oxide, silver oxide, and that reduces the conductivity. So it's typically not used in conduction circuits, but it's a very good conductor. So metals in general are good conductors of electricity because they've got these weakly bonded valence shells that can jump to the conduction band. Things like wood, plastic, and pure water, glass, are very poor conductors. They're called insulators because they don't have these valence electrons that are weakly bonded that can easily jump ship to the conduction band and form that superhighway to generate electric current. So this is the very nature at the atomic level between conductors and insulators. Much more detail is dealt with in the chapter, of course, so quite a bit of significant details to the production of an electric current is talked about, as the reader will have access to for this chapter, and how the energy levels on in a particular atom changes, depending on whether it's the atom is by itself or it's close to its neighbors. Really interesting things happen with these energy levels, and that's shown over here. The energy levels, they begin to sort of take on a more uniform structure right here in a solid, as opposed to if the atom were by itself, the energy levels are substantially more segregated. Insulators, semiconductors, conductors are all dealt with in terms of these energy bands and how they are structured. So a lot of detail went into preparing this chapter on how electric currents are generated from first principles, from atomic structure. Electric currents, current density, for example, valence electrons, conduction electrons, meaning is put to all of it, drift velocity, electric fields, etc. So the reader is going to have quite a bit of information about the generation of electric currents. And so, the sun produces, this is gentoo penguins in one of my trips to Antarctica. That actually has something to do with electric currents. There are several places here. This is close to the South Pole, Antarctica. This is close to the equator in Ngorongoro Crater, Tanzania. That's a Maasai warrior here, my trip there. So people, whether it be penguins, zebras, or Maasai warriors, or myself, wherever you're located, and this is the opposite end of the world, this is close to the North Pole, we're getting to the North Pole rather. This is the Arctic Circle in the far north of Norway. These are some wild reindeers that live up inside of the Arctic Circle. So penguins, zebras, reindeer, myself, we're all subjected to different amounts of radiation from our sun. So depending on your latitude, where you live on Earth, the amount of radiation that's trapped in what's called a solar wind. Our sun produces tremendous amounts of radiation, both in pure energy and particles like high-speed protons, for example. This collectively called a solar wind, and it strikes the surface of the Earth. So I came up with a problem using, from pole to pole, really, some of the destinations I've been to on this planet, for both, I guess, people and animals. What levels of electric current from the solar wind do you get bombarded with depending on where you live on the Earth? It's quite a significant example. It's actually quite cool. I think the reader will get a kick out of how much current the Earth receives just from the sun and the solar wind. And if we're not for the protection of our atmosphere, we wouldn't be here to have this conversation. So it's quite an interesting example. Current densities are dealt with, and some examples about game controllers. Everyone's into video games, so we came up with an example about using video games and calculating, the distance a single electron would move if he were to hold down the power button on the controller for a video game. So it's actually quite cool, and I think the reader, if the reader is a gamer, an avid gamer, would be thrilled, I think, about understanding exactly what happens while they're gaming and not really paying attention to what's going on inside of those conducting wires. It's actually pretty cool. And like every other chapter, there are many different examples that we've come up with, and this one is the Carrizo Plains in California. The North American plate and the South American plate are separated by this flat region here, this salt flat. It's called the Carrizo Plains. So I'm literally standing between two plates, the North American plate and the Pacific plate. There are only a couple of places on Earth where this happens above the ocean surface, and this is one of them at the Carrizo Plains out in California. And so the reason for that particular picture there is to show what's happening right beneath there. The Earth, it has these plates, giant plates, about 24 of them that are floating on liquid rock. And beneath the liquid, there's asthenosphere. And beneath this asthenosphere is a layer of solid rock called a mesosphere. Now, the mesosphere itself is floating on liquid iron, molten iron, semi-molten iron in the outer core. And this molten iron, well, it's a metal, and it's molten, so it's moving, so it's generating an electric current. So I think the average person is completely unaware that very, very deep beneath your feet, thousands of miles below your feet, wherever you're standing on the Earth, is churning molten iron, very hot, several thousands of degrees, and it's producing electric current. Now, there's actually an electric current deep within our planet, and there are actually consequences of that, by the way, as we shall see in a different chapter when we talk about magnetic fields, the origin of the magnetic field of the Earth, and things like the northern lights, the aurora borealis, for example, is due to the molten outer core and that electric current that it generates. So to such an end, we came up with a problem to go down very deep into the Earth. Here's a cross-section of the Earth, and take a small section of this outer core and sort of blew it up over here, and came up with a problem to calculate how much current actually exists deep within the structure of the Earth, far below where humans can ever have access to, at least for many generations to come with the current technology that we have. So it's quite interesting, and the numbers are just absolutely mind-boggling. I think the reader will be blown away by what's happening far below your feet that we're completely unaware of as we go about our daily lives. It's significantly interesting. And like every other chapter, there are several additional problems for the reader to work on to increase proficiency at the end of the chapter. So at the end of this chapter, I think the reader is going to have a good foundation on the nature of electric current, how it's generated, some properties of electric current, current density, for example, drift velocity, and so forth. And it's going to be a good foundation for later on when we talk about things that necessitates fundamental knowledge of the generation of electric currents. Once again, I thank you for your time.